the next thing that we would like to discuss in this course is the so-called Walt Test. You might remember that we have been spoken about the Walt Test already when we were dealing with the technique seemingly unrelated regression. Yeah, so the Walt Test, we needed the Walt Test in order to implement the joint test of the intercept terms, yeah, which is in the literature often referred to as GRS test. Yeah, if you consult the corresponding asset pricing literature. So, and you might remember we needed to implement this joint test, yeah, because of the covariance, yeah, because these parameters, if you estimate the multiple equation model, these parameters here are correlated, yeah. So in the test statistic, this correlation basically enters the test statistic here in the term in the middle, yeah, and our matrices R, they basically depict the corresponding covariances out of this covariance matrix here in the middle. Yeah, you might remember that. So, but now we want to use the Walt test in a single equation model. So again, we use the first stock of the data set and we estimate the following model here. Yeah, so we regress the excess returns of the first stock on a constant, the market factor, the size factor, and the value factor. So we use the simple Farmer and French 3-factor model. Yeah, and because it's a regression equation, we also have here the error term or the residual term denoted as U1t, the error term of the first stock at time t. Then the corresponding hypothesis that we're interested in, is whether the exposures against the size and value factors are jointly 0. What does that mean? So it actually means that if these factors here, if the exposures, if the parameters here both are jointly 0, then it means that the market factor here is the correct model, right? Because then we don't need, obviously, the size factor and the value factor for pricing the excess returns of that stock. Under the alternative hypothesis, at least one of these parameters here is unequal to 0. Yeah? So again, the corresponding test statistic, because we are testing two parameters here, the corresponding test statistic is distributed as chi-square with 2 degrees of freedom under the null hypothesis. Yeah? So that's the formula here. So it's obviously very similar to what we have encountered here earlier for the multiple equation model. Now we have the same formula basically for the single equation model. Yeah, so we have here on the left-hand side, obviously, a term that depicts the corresponding parameters that we are supposed to test. Yeah, and our hypothesis, basically, the zeros here, they enter the equation, obviously, here. And this R, this captures, obviously, the hypothesis, the zeros. And we have, obviously, because we multiply it with itself here on the right-hand side. So this guy here on the left-hand side is obviously, it's transposed. So it's a 1 by t vector times a t by 1 vector. It's a L. If you have two restrictions, then L is 2. So that's a 1 by 2 vector multiplied with a 2 by 1 vector. So we have a scalar, that is basically accounted for by the corresponding covariances between these parameters that we test. And as you see in the middle, what we have here, and if we scroll back, this term was earlier this guy here, because it was a multiple equation model. It was a much bigger, it was a diagonal matrix, right? It's basically the covariance matrix of the diagonal of the whole system of equations. But if it's just a single equation, this guy becomes just the covariance matrix of our parameter estimator, beta hat. And this is given by the estimated sigma square times the regressor matrix transpose times itself inverted. And again, we know that this sigma hat square can be simply estimated by the regression residuals. Yeah, very simple. So how would we implement this test then in MATLAB? So let's denote it. This is our exercise number. Let us see. It's exercise number 11. It's called the Walt Test. So next, first of all, we have to start with retrieving the data vector of excess return for the first stock. Yeah, it's denoted. Let's note it as y1, and we know in the matrix capital Y1 we have stored all of the excess return vectors of our survival stocks, and we want to have the first vector, the first column vector. Yeah. So we have done this before. Let's define our regressor matrix. Yeah, and our regressor matrix, let's see here. Yeah, we have obviously a vector of ones. Yeah, for the constant term that captures the constant term, we need the vector of market excess returns, a vector of the size anomaly, the vector for the size factor, and the vector for the value factor. And we know in our matrix F, yeah, in our workspace, we have the corresponding matrix of risk factors. You might remember that it's here in our workspace. Let's just grab it. It's here. Yeah. If you double click, it pops up here. It's a T/3 matrix, right? So let's define our regressor matrix as a vector of ones that has the dimension T/1. So it's a column vector that has capital T rows, and we add the factor matrix. So what we have here is obviously a T/4 matrix, right? Then our beta, let's denote it as beta 10 because we have already so many betas in our workspace. Let's denote it as beta 10 is then given by our regressor matrix denoted as x10, yeah, transpose times itself. Again, it's the same formula all the time to the power of -1. So it's inverted times regressor matrix transposed times the vector of excess returns from our the asset that we use for these analysis. Then we get the regression residuals because we need to estimate the regression residuals, obviously, because they are a part of the covariance matrix for our beta estimator. Yeah, so we need the regression residuals in order to estimate the sigma hat square here. Yeah, which is a part of the covariance matrix for the parameter estimator that we need for the test statistics. So let's denote the residuals, the residual vector as U10. Yeah, U10 is also obviously a T/1 vector, not obviously. It's defined as the vector of excess returns minus the regressor matrix times the corresponding point estimator. Yeah, this is the our U hat. Yeah? Definition of our U hat. Then our sigma, the corresponding sigma underscore 10, let's denote our sigma hat square, yeah, as sigma underscore 10, which is then simply given by 1 over t minus 5, yeah, because we have to lose 5 observations because we have 5 parameters here to estimate. Well, it's 4 parameters to estimate, so it's actually t minus 4, right? Then divided times what? Obviously U10 transposed times itself. So again, we get here a number, obviously. Then we can estimate now our corresponding covariance matrix of our parameter vector B10, which is then simply given by this guy here, sigma 10 times x10, the regressor matrix transposed times itself, inverted, right? This expression here, obviously, that we have here is the same that we have here. Yeah? So that's the covariance of our point estimator. So then we have to define our R. Yeah, you remember this matrix here, and this is L by K plus 1 matrix. K is 3 because we have 3 regressors, yeah, plus 1 because we have also an intercept term. So K plus 1 is 4. Yeah, and L is 2 because we have 2 restrictions. Yeah, these 2 point estimators should be 0. So R must be, if R is an L by K plus 1 matrix, in our case, R needs to have the dimension 2 by 4. So, and what's the first restriction? So if we have our parameter vector here, so this guy here, the SMB, the exposure against the size vector should be 0, right? So we want to depict this parameter vector out of our beta head vector, which is a 4 by 1 vector, right? Because we have 1, 2, 3, 4 point estimators in our beta head vector. So, and it's obviously the 1, 2, 3. So the third element should be 0. So it's the 1, 2, 3. The third element should be 0. And now you remember that if you write here a colon, then it gives you continues in the next row, basically. Yeah, so it gives you the corresponding dimension. If you write here a comma, it would give you not the correct dimension of the R matrix. So the next one, the next element is the fourth element, right? So it looks like this. Let's just copy that into MATLAB so that you see that R has the right dimension. Let us see what happens here. Yeah, here we need, of course, we have forgotten here, obviously, the multiplication sign, which is a star. So no, it should be correct. Yes, and you see, if you now put an R, let's just wait a second. Obviously, this computer is very slow today. So if you put in R, so what we get is a 2 by 4 matrix, right? This is exactly what we need. So if we, again, if we would put here a comma instead, it would give us a wrong dimension. Yeah, if you write this, the code like this, it gives us one row vector. Yeah, it continues in the same row. So we need to have here a comma so that MATLAB recognizes that we define the matrix as that this part here should be in the next row. Yeah. So now R has the correct dimension, and now we need our small r, this guy here. Yeah, and this is a vector of zeros because the first guy is 0, the second guy is 0. So that's just a simple vector of zeros. Yeah, so it's zeros 2 by 1. Yeah, we could also define it. You see, if you copy it into MATLAB, it would give you this guy, a 2 by 1 vector of zeros. But you could also just write basically R is equal with 0, yeah, because you remember this parenthesis means you define a matrix or a vector, then you write 0, colon 0. Yeah, this gives you obviously the same thing, right? So it doesn't matter how you write it. Yeah, so in both cases it gives you the correct vector that you need for your restrictions. So and now we are ready basically. Now we can implement the Walt test. Yeah, let's call it lambda Walt, and that's simply given by our R, capital R, times what? Times the point estimator, beta 10, minus our restriction, minus R. So what we get is a 2 by 1 vector. We need to transpose it so that it becomes a 1 by 2 vector because we want to have a scalar, right? This is multiplied with what? With capital R, yeah, times the covariance matrix from our point estimator beta 10 times capital R transposed. Yeah, and now we remember that this guy here gives us, it depicts the corresponding covariance terms from the covariance matrix. Yeah. So we multiply it from both sides with, we need to multiply it with both sides from with this R. Yeah. And then we take the inverse times what we have here on the left-hand side, right? Copy that just here, paste it in, yeah, and that's our test statistic. So again, let's copy the whole part here, yeah, that's our test statistic, and copy and paste it here into MATLAB. And what you get is a test statistic of 31.67. Now you remember, under the null hypothesis, what's the distribution for 95% probability and the chi-square distribution with 2 degrees of freedom? We can watch it, we can look it up in the table. And for the chi-square distribution with 2 degrees of freedom, the critical value for 95% is 5.99. Yeah. So obviously the test statistic is much larger than our critical value, which means we have to reject the null hypothesis. Yeah. So our beta exposures against the size factor and the value factor are both jointly statistically significant on a 5% significance level. Yeah. So even if we would take a 1% significance level, yeah, the critical value is 9.2. So even if we take a 1% significance level, still we have to reject the null hypothesis. Yeah. So obviously the exposures are highly significant. Yeah. And what are the exposures? So it's obviously minus 0.45 against the size factor, and minus 0.17 in rounded figures against the value factor. What does it mean? So obviously the stock is a small, it's a big stock, right? Because it's negatively correlated with the size factor, which means it co-moves with the short leg, and in the short leg are big stocks. So that's a big stock. The first stock is a big stock, and it's a growth stock. Yeah, because the exposure against the value factor is negative, which means it co-moves with the short leg. And in the short leg, we know there are growth stocks. So is this surprising? Let's get the t-statistic. Yeah? The t-statistic for the size factor is obviously the corresponding point estimator, which is the third element in our beta hat vector. Yeah, so it's the third element in B10, divided by the square root of the covariance matrix from our point estimator, and it's the square root of the third element, right? So the corresponding t-statistic is obviously minus 5.33 or minus 5.34 in rounded figures. And the t-statistic for the value, for the exposure against the value factor, is obviously the fourth element in our parameter vector divided by the last element on the main diagonal of the covariance matrix for the point estimator, and the t-statistic is minus 1.88. So this guy here is not significant on a 5% level, right? Because this value here is larger than minus 1.96. But this guy here is highly significant. And both jointly, if you test both jointly, they are highly significant, obviously. Yeah. So if we make a single test based upon a single test, we would reject the null hypothesis that the exposure against the value factor is statistically significant on a 5% level. But if we have joint hypothesis, yeah, we have to reject the null hypothesis that these two guys here are both insignificant. Yeah, that's what we conclude. So that's the Walt test. Yeah, you remember we also have been discussing the LM test. Yeah, during the lectures, and this LM test has a different approach. It's a test basically that is under the null hypothesis. You have the model, first you run the model under the null hypothesis. So again, how would we implement the same test using using the LM test, the Lagrange multiplier test. So again, we need to define our vector. We have already done. Actually, we don't need to do it. It's just a redundant step. Okay, we just define our vector of excess returns here. Now let's define our new regressor matrix under the null hypothesis as XX10. And what is it? It's a vector of ones. T by one vector of ones. And under the null hypothesis, obviously, if you're using an LM test, there's just a Markov factor and a vector of ones for the intercept term. So under the null hypothesis, we need to get just the first vector here of our F matrix, because the first vector of our F matrix contains the Markov factor. So that's the regressor. This is the regressor matrix XX1, XX10 is the regressor matrix under the null hypothesis. Okay. So the corresponding point estimator, let's denote it as B11. What's B11? It's obviously XX10 transposed times XX10 inverted times XX10 transposed by our vector Y1. Now we need to get the residuals under the null hypothesis model. Let's denote the residual vector as U11, and it's defined as our excess return vector of stock returns in excess form, which we denoted as Y1 minus the regressor matrix under the null hypothesis, which is XX10 times the point estimator under the null hypothesis, which is B11. So let's just check it out, what we get here. Let's copy this into MATLAB. So what is our B11? Let's retrieve our B11 here. So the exposure against the Markov factor is obviously 0.62 in rounded figures, and the intercept term is obviously 0.5 in rounded figures. This is our point estimator under the null hypothesis. It's a 2 by 1 vector. Now what we need to do is we need to set up the auxiliary regression. You remember, now we use the residuals of the null hypothesis model, and we regress them on the regressor matrix of the alternative model. So the model under the alternative hypothesis. This is what we do. So how does that work? So let's call this parameter vector of that regression as B12. So we have defined earlier here, in this is obviously the matrix of the alternative model. It has a vector of ones and as the first regressor, and the three risk factors of the Farman-Franch three-factor model are also herein. So our X10 is the corresponding regressor matrix of the alternative model. So we could also define it here one more time, but we know it's already in the workspace. We can just retrieve it from the workspace. So we have to regress these residuals here, this residual vector, on the regressor matrix of the alternative model, which we have here. So the corresponding point estimator of that auxiliary regression is B12, and it's then denoted as, or it's defined as X10 transposed times itself inverted again times itself transposed times the vector of regression residuals under the null model. Again, we regress the residuals, the residual vector of the null model on the matrix of the alternative model. We get the point estimator of that, the corresponding point estimator of this regression is denoted here as B11, and this is obviously a 4 by 1 vector, because we know that our X10 matrix, yeah, the regressor matrix under the alternative model, is a T by 4 matrix. Yeah? So this is obviously B1, B12 is then a 4 by 1 vector. So next, we get the regression residuals from the auxiliary regression. Yeah. So how is this vector defined? Let's define it as E11. Yeah. What is it? It's our dependent variable, which is in our case the regression residuals from the null model, denoted as U11, minus the regressor matrix from the alternative, from the times minus the regressor matrix under the alternative hypothesis, yeah, which is our X10, times the corresponding parameter vector B12, yeah, of the auxiliary regression. So next, we have to define the R square, so the coefficient of determination from this auxiliary regression that we implemented here. Yeah. And this is defined as what? It's 1 minus E11 transposed, which is the residual vector of the auxiliary regression transposed times itself, divided by what? Of course, the variation of the dependent variable, which is U11, yeah? It's the regression residuals under the null hypothesis. So the vector itself transposed times itself. Now the corresponding test statistic for the LM test, let's denote it as lambda LM, and it's defined as what? It's T times, it's an asymptotic test, it's T times R squared. So it's the number of observations times the R squared of the auxiliary regression. Okay. So, and hopefully what we get out now is a value very similar to what we have from the Walt test. It would be basically the same. And what you see after running this test here in MATLAB, our LM test gives us a value of 0.2999. So it's rounded 30. Yeah. And you remember under the null hypothesis, this test statistic is distributed as chi-square with 2 degrees of freedom. Again, you remember the corresponding critical value is 5.99, and we come to the same conclusion. We reject the null hypothesis that our exposures against the size and value factors are jointly 0. Yeah? So which means they are jointly significant on a 5% level. So we come to the same conclusion as we came when using the Walt test. Yeah? Let's just copy it one more time here. So the LM test was 30, and the Walt test was 31.67 in rounded figures. So they are very, very close to each other. And this is also the way how it should be. Yeah, because under null hypothesis, they have the same distribution. So now you know how to implement the Walt test and the LM test as well. So finally, we talk about momentum. So what would we like to do? So let's use the first 25 stocks in the data set, and we form different momentum portfolios. So first of all, we want to implement a strategy that is denoted here as short-term reversal effect or short-term reversal strategy. It's a strategy that is long on stocks that had the lowest return in the last month and short on those that had the highest return on the last month. Now, you remember from the lectures that the short-term reversal suggests that those stocks that had performed very poorly in the last month, they tend to outperform those stocks that had performed extraordinarily well during the last month. So the return spread should be around 1% per month. Then in B, we implement a strategy that is based on recent past performance. So we form the momentum portfolio based on being long on those stocks that had the highest cumulative return in the previous 6-month period. And in implementing this strategy, we skip the most recent last months because of the short-term reversal effect. And this portfolio is short on those stocks that had the lowest cumulative return in the corresponding time period. Then the third strategy that we would like to implement, which is basically the standard strategy used in most papers, and it's also used in the paper from Barman Branch, the 2018 paper, as far as I'm concerned, and it's also the strategy that is mostly used in paper from Moskowitz. So that's a strategy that is long on those stocks that had the highest cumulative return in the previous 12 months. And again, we skip the most recent past months when we compound the cumulative return. And this portfolio is short on those stocks that had the lowest cumulative return in the corresponding period. And finally, the last strategy that we would like to implement is a strategy that is long on those stocks that had the highest cumulative return in the periods T-12 until T-7. And we finance this position by shorting those stocks that had the lowest cumulative return in the corresponding time period. And this is a strategy that is discussed or suggested in Novi Mark's paper. And the strategy is based on intermediate past performance. So, and what we do here in our implementation, we will be short in 20% of the stocks, and we will be long on 20% of the stocks. So we have 5 stocks, 5 big stocks from the S&P 500 in each of the legs. Okay. So last is momentum. So first of all, we want to define our matrix. So let's define it as Y5. Let's note Y5, the matrix of stocks that we use. And we want to use the first 25 stocks. We know in our Y1 matrix that we have the excess, the vector of excess stock returns for our survivor stocks, and we want to have the first 25 stocks. So we take all rows, all capital T rows from the first 25 column, from column 1 until 25. So now we have defined our input stocks. The T is obviously the length of that vector. And actually, it's already in it's capital Y5, of course, and actually it's already given here in the workspace, right? So if you write in T here, it's already here in the workspace. So actually, this step is here redundant. So then K is, in this case, K denotes the number of input assets. K is 25. That's the number of stocks. Then we define our N defines the rolling time window. N defines a rolling time window. And you will see how this works out. So next we want to store the results in a matrix. Let's call it results underscore groups is equal with zeros T minus 1 by 3. Okay, because we in this case we operate with 3 groups. So we have the long leg. One group is the long leg. One vector is the group that we skip. The group is that is in the middle, and we have the short leg. So long leg, middle group, and short leg. So then we start our for loop. So we do something from T is running from 1 until T minus N. So we lose, obviously, because we have here this n12 denotes our rolling time window, yeah, because we need obviously, this is what we need because our strategy, it starts at t minus 12. Yeah, these two strategies here, they start at time t minus 12. So we have to go 12 if n, capital N denotes our time where we are now, the time of portfolio formation, yeah, we go maximum 12 months back in time, yeah, when we start to compound the cumulative returns. Here we go only 1 month back, yeah, and here in strategy C and D, we go 12 months. We need to go 12 months back in time. That's why our N is 12. So, and we lose obviously in the end of the sample, in the beginning of the sample, sorry, we lose capital N observations. So that's why our result matrix has the dimension t minus 1 by 3. Yeah. So next we do something obviously for from t is 1 until capital T minus n. And what do we do? Let's create a vector. Let's call it momentum. It's a vector of zero. It's a vector of zeros. Which has a dimension 1 by k. So it's obviously, we store here the cumulative returns for each of the 25 assets, yeah, in a vector. And obviously it has the same, this vector here, it has obviously the same dimension as the y1 vector, because our y1 matrix has the dimension, has 25 columns, yeah? And this vector here has 25 columns, yeah? So it has the same number of columns, and which is also important, which we will see. So now obviously this guy here is in each loop here, when t changes, yeah, this guy is always overwritten. Yeah? So everything that we store in here is after, in each iteration t, this guy here is overwritten. So next, we want to store the corresponding values here in this vector. So we want to store the corresponding cumulative returns for each single asset k here in this vector. That's why our next loop, the next for loop, goes from I is 1 until capital K. So what do? We want to in our momentum vector that has still 0 entries here. Now we put in something here, yeah. So in each entry should be what? It should be the sum from our y5, sum from y5, and we go from t until t plus n. And first we wanted to implement the short-term reversal effect, right? Yeah. So, and today is time capital N. So obviously then we have to start at t plus n minus 2 until t plus n minus 1. It's actually n minus 1. Right? So we are at time capital N, this is 12, in the first iteration. If t is 1, it's actually, this is actually true. It must be like that. So if t is 1, we start at time 1, then we take the sum from 1 plus 12 is 13, minus 2 is 11, until 13 minus 1 until 12. So we take just the monthly return. This means we store the monthly return, yeah, from t minus 13 until t minus 12 in this vector here, in position I. Yeah, where is located stock I? That's what happens here in this loop. So once again, n is 12, yeah, and in the first iteration, we grab what is between the observation 12 and 13, right? Because if t is 1 and n is obviously 12, we have here 11, this becomes 11, and this becomes 12, right? In the second, if t is 2, it would take the next return entry. Yeah, it would take the return from t, then t is 2, it would take the observation 12, the return from 14 minus 2 is 12 until 14 minus 1 is 13. It would take the return from this return and stack it in position I of that vector here. So next we have then ended here this loop. So now we have here, obviously we can copy this into MATLAB already. Copy it here. So, and let's make t to be 1. So we define t as small t as 1, and then we can basically just copy this guy here. Let's copy this part of the code, paste it in. And now what we see here in momentum, in this vector here that we created that had zeros here, when we stored in here the information, what do we find here? It gives us the corresponding vector that we want to have. If we now go back to our Y5, capital Y5, let us see. So what we want to have, let's see one more time. There might be a bugger here in this code. So it's the return that we would like to have is obviously it should be, now we have the sum from 11 to 12, right? But this is not what we want to have. We want to have the return of -8 only, yeah, because this is the previous month's return. So obviously we have to rewrite the code. This would be the correct sign, right? Because it's only this 1 month that we want to have. So it's only this 1 month's return. So let's do it one more time. Let's copy this again into MATLAB. Here is still 1. So now we again let's get the vector of returns. Now obviously it looks much better. Exactly. Now we get exactly, you see, this is exactly the corresponding row that we want to have here. Yeah, it's exactly the same entries that we have here. It's a simple return in that month when the portfolio formation takes place. And now, based upon this return vector here, we sort this whole vector in an increasing order. So, and we buy those stocks that have the lowest return here in this period, in this month, and we buy those stocks that had the lowest return in this month, and we short sell those stocks that had the highest return in this month. And we check, okay, what's the return in the next period, 13? We keep this allocation 1 month ahead. So this is what we want to do now. So we have now defined our corresponding, and the way how we defined this code here, or this part of the code, this is basically the heart of the whole code. And we will see that we just need to make some very small changes here, and we get a completely new momentum strategy. So next, again, we want to sort this vector. Let's call this vector momentum1. Momentum1, and what should it be? Momentum1 is the sorted momentum vector. Momentum. So this command here sorts this vector here in an increasing order. Let's just copy this into Matlab so that we see what's going on here. So this is what happens, right? So here are the highest return entries, obviously. And if we move up a little bit, here, these are the lowest return entries, obviously. And now we buy those stocks that have the lowest 5 returns, these guys here. We want to determine where to find these guys here in the original momentum vector here. Where do we find these guys in this vector here? And where do we find these guys here? Because these are the guys, obviously, these 4 and this 5, we would like to sell, right? Because we want to finance, we want to have a zero cost portfolio. And now we have to determine where to find the corresponding guys here, where are the positions in this vector here. And we know that in this vector here has the same dimension, it has the same positions, that we have stocks in, like we have stocks in the matrix capital Y5, our input matrix. So let's define C1 should be 0.2. So we are now defining the upper bound for the first group, 0.2 times k. K is 25. So on 0.20, 20% of 25 is 5. So this tells us, okay, the 5th position in this vector here, this is the bound for the group number 1. This is the bound for group number 1. So if we go here to this vector, if you say, so okay, C1, let's just copy this. C1 is 5. So what is momentum? If we now plug in momentum from C1, or it's momentum 1 from C1, this is minus 11.8. So minus 11.8 is obviously the last guy, or it's the highest return in the group of stocks that have the lowest returns. So it's the highest return in the group of stocks that have the lowest returns. In the same manner, if we say, okay, what's the highest return, or what's the lowest return in the group of high return stocks? Let's say, okay, let's denote it as C2. Let's denote this value as C2. C2 is equal with 0.8 times K, right? So it's in the position 20. 0.8 times K is 20. It's in the position 20. So C2 is 20. And it's the position, it should be the position 20 of our vector is sorted momentum vector, which is momentum 1, right? Momentum 1 from C2 is 9.88. So 9.88 or around at 9.89 is the corresponding value, here, of the stock that has the lowest return in the high return group. Now we have defined where to find the corresponding return entries. So we say, okay, let's say C3. What is C3? C3 is exactly this value. It's the value momentum. It's the value C1 from momentum 1. And C4 is the corresponding value C2 from momentum 1. This is again, so C4 gives us the value 9.88 and C3 gives us the value minus 11.80, right? So then we say, okay, we need now a vector that shows us where to find the corresponding stocks that are in the first group and in the third group, right? So let's define the stock as group 1. It's equal with zeros, and it's 1 by k, same dimension as our momentum vector, which is unsorted, right? So group 1 is equal to zeros, 1 by k. For 1 is going from 1 until k, do what? So if momentum I, so if our unsorted momentum vector at position I is smaller or equal than C3, and now remember, C3 is again, it gives us the highest return value in the groups of stocks that have the lowest returns, right? So if this is 2, then give us in this position a 1, if the statement is true, and else there should be a 0 in that position, because then it's not a part of that group. So we end the if loop, and we also have to end the for loop. So next, our second group is also a vector of zeros, same dimension, 1 by k. So, and we want to have now the stocks that are in the middle. We want to have those stocks that are not in the long or short leg. So these are all the stocks that are in the middle. So again, we use a for loop for I is going from 1 until k. If momentum at position I, if the corresponding value of this vector at position I for stock I is larger than this value, that we have here determined, which is obviously if it exceeds the largest return for the group 1, and now we have this sign here. So this means that both conditions that come here should be fulfilled, and if the value of momentum I is smaller or equal than C4, which is obviously the lowest return for the group 3, for those stocks that are in the third group. So those stocks are obviously in the middle group. Those that are not a part of the third group and not a part of the second group, yeah, see now here, this obviously is the opposite sign. So obviously these guys are in the middle group, yeah, they should get into, they should have a 1, and otherwise the corresponding stock I should get a 0, because then it's obviously not in this group here. We have to, sorry, we have to AND here this if command, and we have to AND the for loop as well. So, and now we can also determine our third group. Yeah, it's also a vector of, it's a 1 by k vector, yeah, of zeros that we store in the corresponding stocks that are in that group. So again, we start with for loop. For I is from 1 to capital K. Do what? Well, if momentum I is larger than C4, right? Then this corresponding stock should be in that group, so it should get a 1 entry, else group 3I should remain a 0. Let's end the if command, let's end the for loop. Yeah, you see now we have, yeah, all stocks are now somehow allocated, obviously, yeah, into 3 different groups. Yeah. And you see here in the last group, obviously in the third group, here we have the smaller equal sign. If we have here the smaller equal sign, here we need to have the is really larger sign. Yeah. Otherwise, if we would have here this is larger or equal sign, then some of the stocks would be obviously in both groups, and we don't want that. Yeah, we want to allocate each stock only in one of the groups. So that's basically what we have to do. Now we have to calculate the momentum returns for the returns for these that are for each of these groups in the forecast period. Let's define the returns as portfolio 1 for the first group. And how is it defined? So we have to multiply this group 1 vector, which is a 1 by k vector, times what? Times y5. And now we want to get to row capital N plus T, comma, double point. So we have again, so that's now our forecast. Yeah, that's the forecast. So we have created our groups based upon past information. So the information was based upon T plus N minus 1. It was the month T plus N minus 1. So that was the past. So it was just this 1 month return that we basically used here in our sorting procedure, right? So, and our prediction is in N plus 1. It's actually N plus T, right? It's N plus T. In the first iteration, if T is 1, this guy here is the 12 months, yeah, because 1 plus 12 minus 1 is 12, and our prediction is month 13. Yeah. So this is a real out of sample procedure. So now note, our group 1 vector has the dimension 1 by k. So we have to compound the scalar product. So this guy here, if we grab this row here, it gives us basically the excess returns, yeah, of the 13th row. Let's go to y5. Here we have it already in the space here. It gives us basically the whole vector. The whole vector. It's a 1 by k vector. It gives us this guy here, this 1 by k vector of corresponding excess returns of our input assets. So if you multiply it with a binary vector consisting of zeros and ones, So what we get is the sum of all the stocks that are in group number 1. Because if we multiply a vector of zeros and ones, so every 0 entry that we multiply here is a 0, and it adds basically to these zeros these vectors that have a entry of 1 in this group 1 vector. It just adds up these vectors that are in the group. So we have to transpose that row, right? So that this becomes k by 1. Now what we get here is a scalar. It's a 1 by 1. It's the sum of returns that are in this group in the forecast period. So we have to close the parentheses here as well, and then we have to divide it by the number of observations that are in that group, by the sum of group 1. Knowing that there are just 5 assets or 5 stocks in that group, we also could just write here 5. We divide it by 5. Yeah, but let's make it a little bit more professional here. So then let's copy. We can just copy this part of the code. The second group is the group in the middle. It's obviously group 2. And here we have to, so it's group 2 multiplied with the whole row of excess returns. And then it gives us the sum of the stocks that are in the second group divided by the number of stocks in the second group. And then we can copy this here in the next row, and the third portfolio is then what? Well, it's the third, it's group number 3 times the corresponding row vector transposed in the forecast period divided by the numbers of stocks in that group, right? Then we need to store. We want to store these in result group. So in the first row of the first column, we want to store, if t is 1, we store something in the first row and in the first column. And in the first column, we store obviously the corresponding average returns that are in the group of stocks that had the lowest past returns. Then we can just copy this into the next row. In the second column of that matrix result underscore groups, at position t, we store obviously then the excess returns of the group that are in the middle. And in the third column of our matrix result underscore group, at position t, we store obviously then the average returns of those stocks that are in the group that had the highest returns in the previous month. Okay, so that's as simple as this. And now we can hopefully run the code, and let's see. Let's hope that we didn't make any big errors here. Let's copy this into MATLAB. Okay, there's obviously one else command too much. Let's see where we have the error here. It's obviously here. Okay, let's take this away. Let's again copy this code. So now we have run the code. Let's see just, obviously our group 1 vectors, or group 1 plus group 2 plus group 3. They should sum up to 1. If they do, then this part of the code is at least correct. It should be a vector of 1s, and it is. So this means that obviously every stock is only in one group. Whenever you have here somewhere 2, then you have made an error. Okay, then obviously some of these larger or is smaller than equal signs is not correct. So then we have here somewhere an error, obviously. Yeah. So the group 1 plus group 2 plus group 3 vectors should always sum up to 1. So what we can do next is, okay, we have now our short-term reversal strategy. Now we want to know, okay, what's then the momentum portfolio? Okay, the momentum or the short-term reversal portfolio actually, but let's just call it here momentum portfolio in order to keep it simple. What is it? It obviously, okay, we have here now our results underscore groups. Where do we find it? Results underscore groups. So here in this matrix here, yeah, here again we have to think. Here we have stored the predicted returns, yeah, of those stocks, of those 5 stocks basically. The average return of those 5 stocks that had in the previous period the lowest return, or that had the highest negative return, so the lowest returns in the previous month. Here we have those stocks that are in the middle, and here, so here are basically, obviously, if here are 5 stocks in the first group and 5 stocks in the third group, we have 25 stocks in total. Here then are 15 groups obviously here, right? That's the average returns of those 15 stocks that are in the middle. And here in group 3, we have those stocks or the predicted returns, the average predicted returns of stocks that had the highest return in the previous month. Yeah, it's this short-term reversal effect. So we have to buy group 1 and we have to short group 3, right? Because the short-term reversal effect suggests we have to buy the past losers from the previous months and we short sell past winners from previous months. Yeah, so that's our strategy here. So we have to buy. We buy group 1, yeah, the whole vector, double point, minus the third group. Yeah. It is exactly the other way around from standard the standard momentum strategies, right? There it's we would buy the third group, yeah, the past winners, but the short-term reversal effect is different. So then, what's then the mean of that portfolio here? So that's the average return that we would earn if we would implement the strategy for these stocks in the S&P 500. That's the mean of that portfolio. And what's the t-statistic? I want to see, okay, what's the is the payoff significant? So it's basically, it's the mean divided by what? The mean by the square root of the variance of this portfolio, of this momentum portfolio, divided by the length is actually divided by capital T minus n, right? Yeah. So that's it. Let's copy this and we paste it here into MATLAB. So obviously the average payoff is 0.33 across the sample period, and the t-statistic is only 1.08 in round figures, which means that the strategy did not generate payoffs that were statistically significant. Now we can also plot the payoff series. Let's plot this momentum portfolio here. Yeah, we can just use the plot command and then we just in parentheses this momentum underscore portfolio. Now we see the time series evolution of the zero cost portfolio, yeah, the payoffs. So we see here obviously we have here a very high volatility towards the end of the sample, and that's of course as we may guess, that's the time period of the financial crisis, yeah, what we see here. So high volatility going on. For your homework, you could investigate if you cut off the last sample, if you do a sample split, what's the payoff then? Yeah, if you just consider the first part of the sample. maybe it's then something significant might come out. Who knows? So next, what we could do, we could check another strategy. So this was the first part. Yeah, this was the short-term reversal effect. Let's have a look on if we would use, if we would base our cumulative returns on the upon the previous 6 months, skipping the most recent past months. So I told you the only thing that changes here in this code setup is what we have here. That's the heart of the code. So if you want to investigate what are the payoffs then in months from, if today is the capital N, and you would like to go 6 months, we want to have the sum from here. We have to go back -6, right? 7, because if t is 1, then we sum up the returns from 1 plus 12 is 13 minus 7, and we add 7, right? No, it's 6, of course. So we sum up this, we take the cumulative returns, the sum, which means the cumulative returns from here, from t is equal to 6 until t is equal to 12. Yeah. And the predicted return would be then 13. But we need to skip 1 month. So it's then like this, right? So we take the returns from t is 6 until t is 11, and the predicted return is 13 in the time dimension. Yeah. Again, we lose capital N observations, yeah, because we start our portfolio allocation here, yeah, at time capital T, at time capital N. So let's run this code. Everything else remains the same, obviously, so we can just copy here everything. Let's copy this Matlab, let's paste it in. So the payoff is now 0.69% per month, and the t-statistic is 1.88. So on a 5% significance level, this payoff is statistically not different from 0. But if we would have a 10% significance level, this payoff is significant at least on a 10% level, right? Again, we can plot the payoff, and it will probably look very similar. We have a high volatility during the financial crisis period, most likely. Yeah, exactly. And this is what is called the momentum crash. Yeah, that happened obviously in the wake of the financial crisis period. We had here a payoff in a month. There was a month that was the payoff was minus 60%, right? You see here. So we had, yeah, almost 60. Yes, it was around minus 55% negative payoff. So now the next task is we implement this Sumner strategy, yeah, long on those stocks that had the highest cumulative return in the previous 12 months period, and short on those stocks that had the lowest cumulative returns in the corresponding period, right? And now we have to change the code here again. Now we have to take this just away. We have to take t plus capital N minus 12, right? Yeah. Until, so we take the cumulative, if N is capital N is 12 and it starts at t is 1, so we take the sum from observation 1, because this cancels out, until 11. Yeah, this becomes 11. This is exactly what we need to do from 1 to 11. And we skip 1 month, the 12 months, and our forecast is then in month 13, our first forecast. If t is 2, then obviously here we start at, we take this cumulative returns, the sum for stock I from month 2 until 12, right? And the prediction is then month 14. Yeah. So that's the correct strategy. And of course, now we have to remember here, now we buy the winner groups, the winner group, which is the third group, the stocks in the third group, and we short sell the losers, which are in the first group of that strategy here that we defined, right? That's how the momentum strategy is defined. So we can just copy everything again here with the small change in the code here, yeah, in this line. Let's paste it here into Matlab. What comes out is obviously a payoff of 0.26% per month, with the t-statistic of 0.71 in rounded figures, which indicates that this payoff is statistically not different from 0. Yeah. So last but not least, we have a different strategy. Yeah. According to Novimarks, we have to skip like 6 months from portfolio formation. So it takes the returns from the first. We have to estimate the cumulative returns from months t minus 12, which is from the first observation here in the sample until t plus 1 minus 7, right? If t is 1, 13 minus 7, this should work out. Let's see. Let's copy this code again. So what we see now, obviously, we see that this payoff here is statistically significant. Yeah, we have 0.64% per month payoff of our zero-cost portfolio, self-financing portfolio. And the t-statistic is 2.02 in rounded figures, which means that this payoff here of our momentum strategy, according to Novimarks, is statistically significant on a 5% level, because this value here, the t-statistic, is larger than 1.96. Yeah. So we see, obviously, using our subset of stocks in the S&P 500, this first 25 stocks of our sample of survivor stocks, right, and implementing the strategy that Novimarks proposed, based on intermediate past performance, where we basically skip the most recent 6 months in our portfolio formation. If we implement this strategy, obviously we get payoffs. Our zero-cost portfolio generates payoffs that are statistically significant, at least on a 5% level. This is exactly what Novimarks argues in his 2012 paper, right? So now you have learned different momentum portfolios, how to basically write this code for sorting momentum portfolios. So of course there are different possibilities how you can expand this code. You can here take less stocks or more stocks. You can do it depends on what you would like to do. You can widen the spread, you can tighten the spread, you could have more assets, you could check basically, you could have here 10 groups or 5 groups, and of course then this code becomes a little bit more involved, obviously, because you have the more groups you have here in between, so you have basically to modify here this part of the code, right? You have to modify it depending on how many groups or subgroups you have here in between. We have it here as an example. We have kept it very simple. We have only 3 groups. Obviously, if you operate with quintiles, if you have 5 groups, 5 portfolio groups, and you have one long leg and one short leg, then you have obviously 3 groups in between. We have now summarized these 3 groups as group 2, but in most papers you will find also the corresponding payoffs across time of the groups in between, of group 2, 3, and 4, basically. And what people then document, or what they would like to see, is a linear increasing or linear decreasing spread. And if you want to investigate these linear patterns and payoffs, if you sort by different characteristics, then of course you need to expand here on the groups. You need more groups in between. If you have many stocks in the sample, if you have, let's say, 100 stocks or 200 stocks or 500 stocks, and you have deciles, you sort deciles, you have 10 groups, then obviously you have sort of 50 stocks or so in each group, and then you can have well-diversified portfolios in between. You can have 10 well-diversified portfolios where you report the corresponding average payoffs. But we keep it simple here in this example, and that's why we just have 3 groups. And of course, you can write the code also differently. This is just one example. Writing a script or writing a code is like talking a language, and everybody might have a different accent or a different dialect. And so, of course, you can write the code also in different manner, and you might come to the same conclusion, right? So as I told you, this is the heart of the code. If you make here small changes in how you estimate the cumulative returns, that's basically the part of the code where you change which returns, where you basically how you accumulate the returns. Then you can have basically very easily implement different strategies. You can compound the corresponding mean, check the t-statistic of that average payoff, and so on. What you could also do is, of course, you could take this momentum portfolio and regress it on a factor model like the Farmer and French 3-factor model or the 5-factor model, in order to see what happens. Is the intercept term after controlling for other risk factors still significant? Yes or no? So there are many different things that you could do. But that should be everything for this lecture series. Thank you for your attention. Hopefully you learned something reasonable for you, and good luck with the term paper.